Imagine this. High above our planet, invisible particles from the depths of space are raining down upon us. Particles that could annihilate ordinary matter in a flash of energy. These aren't just any particles. They're antimatter, the mirror image of the stuff that makes up everything we know. And the source? A bizarre, spinning remnant of a long-dead star that's been hiding in plain sight for decades. This isn't science fiction, it's the cutting-edge reality of astrophysics as we know it in 2025. As you dive into this exploration, you'll uncover how scientists cracked a mystery that puzzled them for over half a century, why this object is bombarding Earth with antimatter, and what it means for our understanding of the universe. Stick with me through every twist and turn. By the end, you'll see why this discovery isn't just fascinating. It's reshaping our view of cosmic phenomena and could hold keys to even greater secrets. In this detailed journey, we'll break down the science step by step, from the historical detective work that led to identifying this enigmatic object to the latest breakthroughs confirmed just months ago. We'll explore the physics behind antimatter, the mechanics of pulsars, and how this particular star is flooding our cosmic neighborhood with these exotic particles. Along the way, I'll weave in analogies to make the complex concepts accessible, pose thought-provoking questions to keep you engaged, and build suspense around the revelations that await. Whether you're a space enthusiast or just curious about the universe's weirdest wonders, this narrative will pull you in and encourage you to read until the very last word, because the implications extend far beyond our planet, touching on dark matter, cosmic rays, and the fate of stars. As of August 19, 2025, our knowledge of this phenomenon has been updated with fresh data from observatories like NASA's Fermi Gamma Ray Space Telescope and ground-based facilities. Recent analyses, including a 2024 study on gamma-ray halos around pulsars and a 2022 paper estimating Geminga's contribution, have refined our models and confirmed its significant role in the antimatter puzzle. No longer a vague gamma-ray haze, this object, known as Geminga, stands as a testament to human ingenuity in peering into the cosmos. Let's embark on this adventure together, starting with the moment scientists first realized something strange was afoot. Picture the International Space Station, ISS, orbiting Earth at 17,500 miles per hour, a beacon of human achievement against the backdrop of endless space. In 2011, an instrument aboard the ISS called the Alpha Magnetic Spectrometer, AMS-02, started detecting something unexpected, an unusually high number of positrons, the antimatter counterparts to electrons. These weren't trickling in from known sources like radioactive decay in Earth's crust or standard cosmic ray interactions. No, this was a flood, far more than models predicted. AMS-02, a $2 billion particle detector designed to hunt for cosmic rays, antimatter, and even hints of dark matter, had been launched to measure the composition of high-energy particles slamming into our atmosphere. By 2025, it has collected data on billions of events. But back in those early years, the positron excess stood out like a sore thumb. Scientists expected positrons from secondary production, when cosmic rays hit interstellar gas and create particle pairs. But the numbers were off by a factor of several times. What could be causing this surplus? Was it dark matter annihilating itself in the galaxy's halo? Or something more mundane, yet equally intriguing? As data accumulated, patterns emerged. The positrons were high energy, suggesting a nearby source powerful enough to accelerate them to near-light speeds. By 2019, analyses pointed toward pulsars as potential culprits, but it wasn't until refined models in the 2020s that one pulsar rose above the rest: Geminga. Fast forward to 2025, and with over a decade of AMS-02 data, combined with observations from other telescopes, we now estimate that Geminga could contribute significantly to this antimatter excess, potentially even the entire excess at around 1 TeV energies according to a 2022 study. But to understand why, we need to rewind the clock to the 1970s, when Geminga was first spotted not as a pulsar, but as a mysterious gamma-ray glow. This discovery phase hooks us because it mirrors a classic detective story. Clues scattered across decades, false leads, and a eureka moment. As we delve deeper, you'll see how perseverance in science pays off and why staying tuned is crucial. Next, we'll unmask Jaminga itself. As data accumulated, patterns emerged. The positrons were high energy, suggesting a nearby source powerful enough to accelerate them to near light speeds. By 2019, analyses pointed toward pulsars as potential culprits, but it wasn't until refined models in the 2020s that one pulsar rose above the rest, Jaminga. Fast forward to 2025, and with over a decade of AMS-02 data, combined with observations from other telescopes, we now estimate that Jaminga could contribute significantly to this antimatter excess, potentially even the entire excess at around 1 TeV energies according to a 2022 study. But to understand why, we need to rewind the clock to the 1970s, when Jaminga was first spotted not as a pulsar, but as a mysterious gamma-ray glow. This discovery phase hooks us because it mirrors a classic detective story. Clues scattered across decades, false leads, and a eureka moment. As we delve deeper, you'll see how perseverance in science pays off, and why staying tuned is crucial. Next, we'll unmask Jaminga itself. Jaminga isn't a household name like the Crab Nebula or black holes, but it should be. Located about 800 light-years away in the constellation Gemini, hence its name, a blend of Gemini gamma-ray source and a Milanese dialect phrase meaning it's not there. This object has eluded easy classification since its discovery. First detected in 1972 by NASA's Small Astronomy Satellite 2, it appeared as an unidentified gamma-ray haze, one of the brightest in the sky yet invisible in optical or radio wavelengths at the time. For years, astronomers scratched their heads. Was it a distant galaxy, a black hole, or something closer? By 1976, Italian astrophysicist Giovanni Bignami coined the name Jaminga, capturing its elusive nature. It wasn't until the 1980s, with X-ray observations from satellites like Einstein, that pinpointing began. In 1983, faint X-rays narrowed the location, but the breakthrough came in 1991 with the Rosat X-ray telescope and the Compton Gamma Ray Observatory's EGRET instrument. They revealed pulsing signals, X-rays and gamma rays flickering every 0.237 seconds. Jaminga was a pulsar, a rapidly rotating neutron star. Neutron stars are the ultra-dense corpses of massive stars that exploded as supernovae. Jaminga's progenitor, several times the Sun's mass, went supernova around 350,000 years ago, compressing its core into a sphere just 20 to 30 kilometers across, but packing 1.5 solar masses. Spinning at 4 times per second, Jaminga emits beams of radiation from its magnetic poles, like a cosmic lighthouse. But unlike typical pulsars, it's radio quiet at higher frequencies, only whispering faint radio signals below 100 megahertz. Detected in 1997 by Russia's Pushchino Radio Astronomy Observatory. Why the silence? Jaminga's magnetic field and spin axis alignment mean its radio beams barely graze Earth, while gamma-ray beams hit us head-on. This makes it the archetype of gamma-ray pulsars, with 99% of its energy output in gamma rays. As of 2025, over 300 gamma-ray pulsars are known, thanks to NASA's Fermi mission, but Jaminga remains a standout due to its proximity and power. Intrigued yet? This bizarre object's story gets even more captivating when we explore how it generates antimatter. Keep reading. The mechanics will blow your mind. Before we connect Jaminga to the antimatter barrage, let's demystify antimatter itself. In the realm of particle physics, every particle has an antiparticle with opposite charge but identical mass. Electrons have positrons. Protons have antiprotons. When matter and antimatter meet, they annihilate, converting entirely into energy per Einstein's E equals mc squared, far more efficient than nuclear fusion. Antimatter isn't just theoretical, it's produced in particle accelerators like CERN's Large Hadron Collider, where scientists study it to understand why the universe favors matter over antimatter, the baryon asymmetry problem. In space, Antimatter arises from high-energy processes, cosmic rays smashing into interstellar medium, or even thunderstorms on Earth creating positrons via gamma-ray flashes. But the excess hitting Earth? That's cosmic in origin? Positrons from space interact with our atmosphere, producing secondary particles detectable by instruments like AMS-02. The danger? Minimal. Earth's magnetic field and atmosphere shield us, absorbing most energy. Ground-level exposure is negligible, part of the natural radiation background, about 2.4 millisieverts per year from cosmic rays, per 2025 IAEA reports. No cause for alarm, it's science's gain. Why engage with this? Because understanding antimatter unlocks universe secrets, like the Big Bang's matter dominance. Jaminga's role ties into this grand puzzle. Next, how it forges these particles. Pulsars like Jaminga are nature's particle accelerators, dwarfing human efforts. Jaminga's magnetic field, a quadrillion times Earth's, twists and snaps, accelerating charged particles to relativistic speeds. Electrons and positrons spiral along field lines, emitting synchrotron radiation in radio and X-rays. The antimatter magic happens via pair production. High-energy gamma rays from the pulsar's magnetosphere collide with lower-energy photons, starlight or cosmic microwave background, creating electron-positron pairs. These pairs get further accelerated, cascading into more pairs, a multiplier effect. Jaminga's Pulsar Wind Nebula, PWN, confirmed in 2005 by Chandra X-ray Observatory, is key. Plasma winds from magnetic poles slam into surrounding gas, creating shock waves that boost particles. By 2017, the High-Altitude Water Cherenkov, HAWC Observatory, spotted a gamma-ray halo around Jaminga, spanning 20 degrees at 10 TeV. Vast, like 40 full moons. Updated in 2023 with Fermi data, analyzed by Mattia Di Mauro's team, this halo confirms escaping positrons diffuse outward, some reaching Earth. In a 2022 study, researchers refined the injection spectrum to a power law with a spectral index around 1 and a cutoff at 100 tera-electron volts, suggesting Jaminga alone could account for the entire positron excess at 1 tera-electron volt energies. Jaminga's high speed, 210 kilometers per second, through space creates bow-shock structures, enhancing emission. This process bombards Earth with positrons, but why the debate on its full contribution? The suspense builds. What does this mean for us? The impact on Earth, antimatter rain, and scientific insights. Earth is under constant cosmic bombardment. Protons, electrons, nuclei, but antimatter adds intrigue. Positrons from Jaminga annihilate with atmospheric electrons, producing 511 kiloelectron volts gamma rays, detectable but harmless. NASA's Fermi and AMS-02 data show this flux peaks at certain energies, matching pulsar models. In 2025, with solar activity at solar cycle 25's declining phase, peak in 2024, cosmic ray influx increases as the sun's magnetic field weakens, allowing more positrons through. No health risks. Annual dose from all cosmic rays is less than 1 millisievert, per UNSGEAR 2025 report. Instead, benefits. Studying these particles refines dark matter searches. If excess were from dark matter, we'd see different spectra. Pulsar origins fit better. Jaminga's supernova 350,000 years ago might have influenced prehistoric Earth, depositing beryllium-10 in ice cores linked to climate shifts. Today, it's a lab for astrophysics. But wait, recent twists in 2024 and 2025 data challenge assumptions. Stay engaged, the latest discoveries await. As of August 19, 2025, the antimatter story evolves. NASA's Fermi mission, operational since 2008, released updated halo maps in recent analyses, showing Jaminga's gamma-ray bubble larger at lower energies, supporting positron diffusion models. A 2024 review in La Revista del Nuevo Cimento on gamma-ray halos around pulsars emphasizes the suppressed diffusion, 2 to 3 orders of magnitude lower than galactic average, around Jaminga, impacting models of particle transport. This suggests that while initial 2017 HAWC data implied pulsars might not fully explain the excess due to slow diffusion, two-zone diffusion models, low diffusion near the pulsar, transitioning to standard ISM diffusion, could enhance the positron flux reaching Earth, reconciling observations. Cross-correlations with AMS-02 data, building on 2022 estimates, attribute a substantial portion of the positron excess to Geminga, particularly at high energies around 1 tera-electron-volt, where it might explain the entirety. Ground-based arrays like HAWC and LHAASO provide, to appreciate Geminga, compare to Crab pulsar, younger, radio-loud with visible nebula. Geminga's age, 350,000 years, means cooled, radio-faint. Antimatter elsewhere, Fermi detected annihilation signals in gamma-ray bursts, like BOAT in 2022. Thunderstorms produce terrestrial gamma flashes, creating positrons, nature's mini-accelerators. Dark matter ties. WIMPs might produce positrons, but pulsar fits better. 2024 studies rule out some models, favoring astrophysical sources. Cosmic rays overall, 90% protons, but antimatter fraction tiny, yet informative. Pulsars discovered 1967 by Jocelyn Bell Burnell, initially little green men. By the 1970s, gamma-ray astronomy boomed with SAS-2. Geminga's timeline, 1972 detection, 1991 pulsar ID, 1997 radio pulses, 2005 PWN, 2017 halo, 2022/2024 refinements. Heroes, Bignami, Halpern, Caraveo, decades of dedication. Not all agree pulsars explain everything. 2017 HAWC results suggested slow diffusion limits reach, but 2022 and 2024 models with two-zone diffusion counter this, showing potential for full explanation. 2024 debates. Positron spectrum bump at 300 GeV, pulsar, or exotic? Fermi data leans pulsar, but if halos are common, might overshoot flux unless efficiency's low. Systematics. Interstellar magnetic fields bend paths, complicating tracing. Upcoming, CTA, Cherenkov Telescope Array, online, 2026, probing TV halos. Multi-messenger, gravitational waves from pulsar mergers could link. Antimatter propulsion dreams, harvesting cosmic positrons, sci-fi now, but inspiring. As we look forward, the evolving models of diffusion and particle injection promise to clarify whether Geminga and its kin are the sole architects of the positron excess, or if unseen forces like dark matter play a hidden role. Imagine the breakthroughs awaiting with next-generation telescopes, detailed maps of halos that could pinpoint exact diffusion zones, revealing how these cosmic engines sculpt the galaxy's particle landscape. This ongoing research not only deepens our grasp of fundamental physics, but also inspires wonder about our place in a universe teeming with energetic mysteries, urging us to keep exploring, questioning, and anticipating the next revelation that could redefine reality. Moreover, the implications for technology and society are profound. Understanding antimatter production in space could pave the way for advanced energy sources or propulsion systems, turning science fiction into feasible future innovations. By staying engaged with these developments, we participate in humanity's quest to unravel the cosmos, fostering a sense of connection to the stars that encourages lifelong curiosity and a commitment to scientific inquiry. Geminga, this bizarre pulsar bombarding Earth with antimatter, embodies cosmic wonder. From elusive gamma source to antimatter factory, it teaches resilience in science. As you reach the end, reflect. Universe is full of surprises. This story encourages exploration. Share, discuss, look up. The cosmos awaits.